So in differential equations, we talk about solving a DE by, if possible, separating the variables. That might not be possible all the time. Typically, and what I want you to see in the pedagogy of this course is that the first section that we come to in terms of actually solving a differential equation is separation of variables. And then from the next section and the next section is the idea that when you're given a differential equation, your first step to see if you can solve is separation of variables. Okay? That's typically the easiest one. So if that works, if you can solve it based on that, fine. If not, then you move to the next idea. So as we go with these sections, the idea, and this textbook is somewhat different than the classic textbook for differential equations. In the classic version, he has the order precise, what I would prefer. In this edition, which he tries to introduce more modeling problems, the sequence is not typically the order, but what I will do is getting close to the test, and we go over problems to review, I will give you that order. Like if I'm given a differential equation, you have no clue about how to solve it, first can I do this, separate the variables? Does that work? If not, the next step would be, is it possible that this differential equation is said to be homogeneous? That'll be the next thing. If it's homogeneous, I solve it based on that method. If not, I move to the next level. And I'll show you all of that so that when you're given a differential equation problem, you want to be able to, in your mind, work through those sequences. Can I do this? The easiest first. If not, can I do the next one it's not as easy, but it's doable. And then if that doesn't work, then the next one. So you have, like, say, for example, here, 5 methods that we'll cover in Chapter 2. 5 methods of solving a differential equation. Try 1, try 2, try 3, try 4, try 5. If it's a first-order differential equation, with those 5 techniques, you should be able to solve it, okay? And then we move from Chapter 2, we get to Chapter 4, then we'll talk about second-order differential equations. I'll give you methods there. We'll start with the ground 0, 1. Does this method work? If so, use that. If not, go to the next one, okay? So here, to separate the variables, the idea simply is to collect like terms, get like terms together. Get the x's, dx's together, get the y's, dy's together. So first order simply means that it's a differential equation or an equation with a derivative to the first power. So dy over dx is just y prime. So dy over dx equal to g of x, h of y. If it's in that simplified form, then notice that it's possible to multiply the dx to both sides, and then there I would have g of x, h of y, dx, and then divide both sides by h of y. So that means I can get the y with the dy together, and then I get the x with the dx together. So if that's possible, we separate the variables. Now, the problem happens is if I have a plus something else over there, then more likely I will not be able to separate the variable. So if it's something simple, this quantity equal to something else, and then we can divide, multiply, collect like terms, get the x's on one side, y's on the other side, or it could be y's on one side, t's on the other side. Okay? But as long as we can separate the variables, then we can solve based on this method. Let's look at number 1. Solve by separating the variables. Note here. The idea is it possible to get like terms separate and together? So to get like terms together. If so, then we can use this method. So here, number 1, have dy over dx, a derivative that is seen as a ratio of differentials. Dy is a differential, the change in y and dx, the somewhat slow change, the tortoise change of the so-called variable. Newton called it the infinitesimally small change, dy over dx. These differentials, we can separate them. So I can multiply both sides by dx. So when I do that, we say this implies that dy is equal to sine of 5x dx. Now once you've separated the variables, we integrate both sides, each side with respect to its differential. So here, integrate the dy is equal to the integral of sine 5x dx. So you integrate dy, you get what? Y. Then you integrate sine of 5x dx, you get what? Everybody except Nazareth. What do you get? Wow, this guy is great. That's right. Negative 1/5 cosine 5x plus c. So here we get y is equal to negative 1/5 cosine 5x plus c. All right. Why the negative? Because the integral of sine is what? Negative cosine. So now, secondly, why the 1/5? Pardon me? I mean, but why? Because of 5x. So, I mean, but why? What method did you use to be able to get the 1/5? Huh? Well, the chain rule applied to an integral. The chain rule with respect to derivatives would be one way, but here we're integrating, right? So what's the chain rule? That's a good thought. What's the chain rule applied to integrals? We call that what? U du substitution. That's exactly what you use, right? You let u equal to 5x, so du becomes 5 dx, right? So then you get what you want. So that u equal to 5x. This implies that du is equal to 5 dx. But you want to isolate to get the dx. So the dx would be 1/5 du. Is equal to dx. So there we have the y on the left side is equal to the integral of here the sine u, and then the 1/5 du represents the dx. And so you have y is equal to 1/5 times the integral of sine u du, and then the integral of sine is the negative, and so the y is negative 1/5 cosine here u, or 5x plus some constant. Okay, everybody fine with that? Now that tends to be the play, especially for integration, is to remember that if you have in your the so-called integrand, if you have a derivative of a function, derivative of an expression, then you want to be able to use a u du substitution to integrate. Right? So let's look at this next one here. So here we say this implies that if I subtract both sides by the dx, so I have this e to the 3x dy is equal to negative dx. But the e to the 3x, it's an unlike term with respect to dy. So I'm going to divide both sides by e to the 3x. So here I get dy is equal to that negative over there, e to the negative 3x dx. So now the variables are separable. We have the y's together, we have the x's together. Now simply integrate both sides respectively. So we have the integral of dy is equal to negative times the integral of e to the negative 3x dx. And so here the integral of dy is y. The integral of, when I integrate e to the u, I got to make sure that I have du here. Now that u is connected with du. If I have u, I got to have this derivative there as well. If not, then I use the substitution, right? The u du substitution. So in order for me to get this guy. Well, notice here that u is negative 3x, but du is negative 3 dx. So I don't have that, I have just a dx, right? So that's why you know that you have a fraction in your result. So let u equal to negative 3x. So du is equal to negative 3 dx. So that implies that negative 1/3 du represents that dx. So here we have y, this y, the integral of dy is equal to, here, I have that negative already there, and then I have negative 1/3 times the integral of e to the u du. So here, this integral of e to the u du just gives me e to the u plus c. So this is parentheses. It's better to write with chalk. So here we get y is equal to, negative times negative goes out, it's just 1/3. And this is times e to the u, but u is negative 3x and then plus some constant c. Okay. So very straightforward, nothing fancy. You've seen this before from Calculus 2. Let me note here these steps for separation of variables, just to make sure you got it. To solve by separation of variables. So the first thing you want to do, if possible, is to get the terms, the like terms together. So get here associating x with dx and then y with dy. And then number 2, integrate with respect to dx or with dy. Let's look at some more problems. So here we have x dy dx is equal to 4y. So what I'm going to do is to go ahead and, do you see, to multiply both sides by dx, divide both sides by x, divide both sides by y. And that'll give me the y's with the dy's together x's with the dx's together. Right, so we do all that in one stroke because we can do that. So I have 1 over y dy is equal to 4 over x dx. Is that okay? Okay. So now the variables are separable. So now we integrate with respect to dx and with respect to dy. And then after a while, you'll be able to just, instead of having to write that like Nazareth, you can just write the answer. You can look at the answer. That's natural log of y is equal to 4 times the natural log of x plus some constant. So that's the goal. So here. So we get here the natural log of the absolute value of y is equal to 4 times the natural log of the absolute value of x plus some constant. Let's call it c sub 1. So here, this is the natural log of the absolute value of y is equal to the natural log of x to the 4th plus some constant, c sub 1. Now here you can exponentiate both sides. To do that, that gives us the y by itself. We want to be able to write y is equal to. Now sometimes you might not be able to do that, to explicitly state y by itself. But if you can, by all means do that. And in some variations, sometimes, they may take the natural log of that constant as well. I mean, that's fine if you do it, or if you don't do it, I mean, that's okay. Sometimes in some circles, they may write it, the natural log of y is equal to the natural log of x to the 4th plus the natural log of c sub 1. And then exponentiate everything everywhere. So here we exponentiate this, we get e to the natural log of y is equal to e to the natural log of x to the 4th. And that's up top plus that constant. So here we get y is equal to c times e. Well, this e to the natural log of x to the 4th is just x to the 4th. Let's just write that. And here, where c is equal to e to the c sub 1. Okay. So this is our answer. Is everybody with me so far? All right. All right. Let's see if you can take a stab at number 7. See if you can do that one. It's dy over dx. Let me get that pen shape out the way. Dy over dx is equal to e to the 3x, and then there's plus up top plus the 2y. So e to the 3x plus 2y. Let's see how you fare with that. So here, we can write this, ooh, no, not red. So this is dy over dx is equal to e to the 3x times e to the 2y. Multiply both sides by that dx, and then divide both sides by e to the 2y. So here we get e to the negative 2y dy is equal to e to the 3x dx. Did you get that? That's like, it's like half your troubles. Right? So Now we integrate. We do not hesitate. We integrate. So do a u du on that e to the negative 2y, and also do a u du on that e to the 3x. So here, you kind of know what's happening. So this is negative 1/2 times e to the negative 2y is equal to 1/3 times e to the 3x plus some constant. Right? That's a negative there. Now, if you want, so I think the back of the book has it where they have the e to the negative 2y by itself. So they just multiplied everything by negative 2. So he has something like e to the negative 2y is equal to here negative 2/3 times e to the 3x plus c. Multiplying a constant times a constant is still a constant. So multiplying negative 2 times c is still going to be a constant. So that's fine.
Is there other ways to do something like a step 2 exponential functions like that? Would that be really different?
Yeah, if you could get both of those guys on the same side, but the only problem with that is once you take the natural log of that plus sign or that minus sign that separates them, you wouldn't be able to go in there and do anything with that. It'll still be a sum or a difference. Yeah. So my thing is, the best thing is probably to leave it like that. Yes, sir. Yeah. Again, you could exponentiate just how it is. I mean, that's fine. And that'll leave you with negative 2y is equal to, you have to take this guy and make this a power up there. So that'll be negative 2y is equal to 3x raised to the power of negative 2/3, and then times some constant over there. Yeah, you could. Yeah, you could. But just be very careful. I tell my classes every year in differential equations, you can go further, and that's what we want you to do. Try to go further. But if you're unsure about what you're doing and going further, well, you stop where you're sure, and I give you credit where you're sure. But if you go even further, and then it becomes unsure, then I take off points. Okay? So again, we encourage you to go further. So, let's see, number 15. You see, that's a direct problem from the previous ones. I want you to see that parallels what we've already seen. Let's go to 17. It's a little bit more to that one. Because again, with number 15, you separate the variables. That'll just give you 1 over s ds is equal to k dr. Integrate both sides. Once they give you the natural log of the absolute value of s is equal to k r plus some constant. Exponentiate both sides. That looks like basically in section 1.3 we talked about those population growth and decay problems. It's the same setup, right? Exponentiate both sides. We get s is equal to some constant times e to the kr. So nothing fancy there. But 17. 17. Okay. So a couple of things we do at once. We multiply both sides by dt. Then secondly, divide both sides by p minus p squared. See that? To get the p's together. And so when we do, we have 1 over, I'm going to go ahead and do some factoring. P minus the parentheses 1 minus p times dp is equal to dt. So now we have the variable separable, so we integrate both sides. So what's your proposition to integrating 1 over p times the expression 1 minus p. Shh. Boy, I tell you the truth. Women. No, I'm just joking. I'm being quiet. I talking to you. Class. What is our proposition to solve that? Remember, this class uses heavenly calculus 2. I told one class last semester I'm going to get somebody to make me a paddle and bring it up here. That's back. I don't know what that is. No. What's a method in calculus 2 that we have that you can solve something like 1 over, it can be 1 over x minus 2 times x plus 3 or something like that. What's that method called? No. We have some later that will, but not this one. Do you see it? Now here's the good thing. In class now, because we're not getting tested, you can talk and be wrong, and that's okay. But test day, you want to be right. Yes. You about to say partial fractions, decomposition? No, you about to say partial fractions. Yes, partial fractions decomposition. That's the way that I would break that down, right? Yeah. Now that right side is just t, but this left side is what we're working on. So this is 1 over p times 1 minus p is equal to some a over p plus some b over 1 minus p. Do you remember that? Multiply both sides by the LCD, which is p times 1 minus p, and that implies then that we have 1 is equal to a times 1 minus p plus, what in the world? BP. So 1, if we let p equal to 0, that implies that 1 is equal to a. And let p equal to 1, cancel out one variable to solve for the other, or the we call it a and b, the generic constants. So if we let p equal to 1, that'll get rid of a, we can solve for b. That implies that 1 is equal to, that's 0, and then p is 1, so we get b is equal to 1. So a is equal to 1, and b is equal to 1. Right? So now what we have is that left side is the integral of 1 over p plus 1 over 1 minus p. I'm going to get you on this one right here. I'm going to get you, watch. So that's equal to the integral of the dt, just write t, some constant there. So I integrate the left side, and that gives me what? I'm writing what you say. I get. I said, shh. So what do we get? Huh? 1? Just something. Sir? Wouldn't that be nice? Everything equals to 1. We just go home, right? What's the integral of 1 over p dp? You integrate this, then plus the integral of that. What's the integral of this? Well, yeah, natural log of p. Right? Now, what's the integral of 1 over 1 minus p dp? This is where I get them. This is where I get them. What's that?
Instead of cross fraction, can we just separate them by, like you can say 1 over p plus 1 over 1 minus p. You don't have to go through the partial fraction.
You saying up here?
Yeah. No, the bottom one. Like you put 1 over p times 1 minus p. Over there, when you did the
Right
partial
here.
fraction. Instead of like going from a partial fraction, can you just do 1 over p plus 1 over 1 minus p?
Well, how do you know that a and b is equal to 1?
Well, we have 1 over p multiplied by 1 minus p.
But not necessarily, because it could be one of those guys could be a negative. If this was a plus sign, if there was a plus right there, then the signs for a and b would be different. So you just can't jump to that. You got to have mathematical reason for every step that we do, right? Just because we feel like something. That's right. So again, what's the integral of the natural log of 1 over 1 minus p? Did you hear that, class? The natural log of 1 minus p. This is minus the natural log of the absolute value of 1 minus p. It's equal to t plus c sub 1. Why is it a minus? Because that'll get you. That's going to get you. That's going to get you. Why is it a minus right there? 1 minus p. You have to let u equal to 1 minus p. du is negative dp. Negative. See that? God gets you every time. Got to have your eyes open. Right? So this becomes the natural log, yes, of p all over 1 minus p is equal to t plus c sub 1. Now we exponentiate both sides and come over here. So I get p over 1 minus p is equal to some constant times e to the t. So I want to stop there, but look, but the answer is that. Are they the same? And if so, show me. Here's the answer that I got up there. Here's the answer in the back of the book. Well, they're the same. And if so, can we show that they are? Can I go from what I have up there to this? And as a matter of fact, do you see what they did? They just got p by itself from that previous answer that I have. How do you get p by itself? Take what I have here, right? Multiply both sides by 1 minus p. So you get p is equal to, yes, c times e to the t times 1 minus p. Right? You come down here. Let's put it here. So this is p is equal to c times e to the t. Distribute the c e t minus c e to the t times p. Right. Now get the like terms together. So this is p plus c times e to the t times p is equal to c times e to the t. Factor out of p, I have 1 plus c times e to the t. Do you see it now? It's equal to c times e to the t. So p is equal to c times e to the t all over 1 plus c times e to the t. See that? Okay. Now, on the test, you can just give me that. I'm fine with that. All right? I'm fine with that. Because they're equivalent. Right? I mean, but saying something is equivalent is one thing, but being able to show that they're equivalent there's another. So if you know that, then you can just give me one or the other, and I'm satisfied with that. Are you in my class? Okay. I mean, but why are you concerned about a problem when it's the concept that you know? You know the concept. See, I got to go back and change Weber sign because in my calculus 1, 2, and 3, people are just memorizing problems, and they see that problem on the test, they get it right because it's not the concept that sometimes we know, it's the memorization of steps. But you got to be able to know it, right? So if we change the problem up, can you solve that? I can't do that. I've never seen it before. But that's what life is all about, right? Just because you hadn't seen it before doesn't mean that you can't do it. You got to still challenge it and conquer it, right? Yes, sir. Integration on which one? This part right here. Okay, 1 over p times 1 minus p. You see how we broke that down? That was by partial fractions. Right? Did you get that part? Okay. So 1 over p times 1 minus p, you want to integrate that. How do you integrate that? Well, back in the integration techniques in chapter 8 of calculus 2, you went through several, scenarios. Is it direct integration? Can I do that? Well, no. Is it du substitution? Can I use that? If not, then the next one was, is it a fraction? Can I divide and then simplify? Well, I can't do that. It's already a proper fraction. So then the next one was, can I use integration by parts? And then the next one was, if I can't use integration by parts, well, can I solve this by partial fraction decomposition? And that falls in line with partial fraction decomposition, right? And so the denominator is broken up into linear terms. P is linear. 1 minus p is linear. So for partial fraction decomposition, you say that based on how many terms that I have in my denominator, you have 2, right? So that means that I'm going to have 2 generic constants, a and b. Why are they constants and not anything else? Well, the difference between the numerator and denominator, when you divide, there has to be a difference of 1. So if my denominator is linear, because I know it is because I'm getting this p from here, it's to the first power, so the top guy has to be a constant number, right? If this was x squared, I got to have x up top, right? So the same thing here, 1 minus p is linear, so the numerator got to be a constant. It has to be different from this guy, so that's why we have some a and some b. And so now after that, all you're doing is just doing algebra, multiplying both sides by the LCD, right? And so when you do that, you have the 1 here is equal to a times 1 minus p, and then plus b times p. Now you're solving for a and you're solving for b. So a very simple technique was to solve for a, you take this p over here and see if you can cancel it out. Well, how do we cancel out that p? That p, if it's set to equal to 0, this cancels out. So I can cancel out one term to solve for the other term. So let p equal to 0. If p is 0, just plug in everywhere we have p for 0, and then you end up with 1 is equal to a. And then the next one, how do I solve for this b over here? Well, I come over here and let this p equal to 1, because 1 minus 1 is 0. That'll cancel out the a. So here we let p equal to 1, so I get 1 is equal to a times 0 plus b is equal to 1. So now I plug in, the a is 1, that's 1 over p. I plug in the b, 1, that's 1 over 1 minus p. You integrate 1 over p, that's the natural log. You integrate this guy, it's the natural log of 1 minus p, but you got to take into consideration this 1 minus p. If I let that equal to u, du becomes negative dp. So it's a negative sign out here. Right? And then you can combine these two by the property of natural logs. That becomes the difference becomes the ratio, right? And then exponentiate both sides, and you get what you need. Right. So let's look at the next one. Oh, this is good. So what color is that? So again, we're going to get the dx on the opposite side. What I'm going to do here is, instead of having a fraction, I want to try to write both sides until I have some expression is equal to some other expression. So I'm going to multiply, or just cross multiply, if you will. And so what I have here is x, y, minus 2x, plus 4y, minus 8. That's times dy. That's equal to x, y, plus 3x, minus y, minus 3. And that's equal to dx. All right? No matter how difficult the problem may look, I think you want to just look at the terms that you have, and you can always take something that seems to be big and try to break it down into parts. So that's the idea that we employ. Look at the xy minus 2x. They have a common factor of an x, so I can factor out an x there. You look at 4y minus 8. They have a common factor of a 4, so I can factor a 4. You come over here, xy plus 3x. They have a common factor of an x, so I'm going to use the distributive property. And then over here, minus y minus 3, they have a common factor of a negative 1. So once you do that and then see what you have after that, and it kind of flows like butter. No? Okay. So this is x times y minus 2 plus 4 times y minus 2. Here, this is all times dy. That's equal to, come to the other side, factor out of x. Uh-oh. So we factor out of x there. We have y plus 3. Then we factor out of 1. We have y plus 3. That's all times dx. So the y minus 2 is a common factor, so I factor out a y minus 2. Let's have left x plus 4 times dy is equal to, you can factor on the right side, a y plus 3 is common. Have left x minus 1 times dx. So now I want to separate the variables. So now it's in a meaningful manner that we can get the x's and dx's together. We can get the y's and dy's together. So here, I'm going to leave that y minus 2 there because I have a dy right there. But I don't need that x plus 4 there, so I'm going to divide both sides with x plus 4. And then on the right side, I have that y plus 3, but over here is a dx. I'm going to divide both sides by y plus 3. So what I have, yes, is y minus 2 all over y plus 3 dy is equal to x minus 1 all over x plus 4 dx. So now the variables are separable, so now we integrate. So integrate the left side with respect to y, and integrate the right side with respect to x. So look, we just do that, right? Everything else is set up for us. So what is the integration technique here? Again, this is a copy of Chapter 8 in Calculus 2. There's a couple of ways you can do that. The way that I prefer is what I had discussed in Calculus 2. It's a fraction, right? It's y minus 2 divided by y plus 3. Is it proper or is it improper? You want to say proper? I know, we want to say proper, but it's improper. We want to say, I'm with you. How come it can't be? I want to be proper, You're from where I'm from in South Alabama, we're improper. We have to go to these fancy churches and these meetings. We got to dress right, and, I got to make sure my subject and verb agrees. Got to be careful in how I talk. Yes, sir, and no, sir. You can't wait to get back outside so you can just say whatever you want to say. but it's improper. All right? It's improper. Why? Now, if it was numbers like, let's say, okay, I got this. 5 over 3, is that proper or improper? 5 over 3. 5 divided by 3. It's improper, right? Because 5 is bigger than 3. Because you can write 5 over 3 as 1 2/3, right? So the 2/3 is said to be proper. So a proper fraction is said to be where the numerator, its degree is less than the degree of your denominator. Here, my degree up top is y to the first power. My degree downstairs is y to the first power. So it's said to be improper. If my degree up top is the same as the bottom or higher than the bottom, and a lot of times you're used to seeing that like y to the second divided by y. You say that's improper. But it can be y divided by y. That's still improper. Because you want to have, if you have y downstairs, you want to have just a number in the numerator. Right? So we said in calculus 2 that when you're integrating an improper algebraic expression, you do what? Anybody remember? You said divide. Yes, sir. Is it Cameron? What's the name again? Yes, sir. John, last name? That's right, John. That's right. John is very smart. I used to have a prize over here. I used to give the students when they got something right. I got to look for my prize. And John, you get a prize, man. Yes, sir. So here, this improper fraction, right? We divide the bottom into the top. Same thing over here. It's also improper, right? X minus 1, the power of x minus 1 is the first power. The power of x plus 4 is to the first power. So we have to divide. Improper rational expressions, to simplify, we divide. Okay? So if that's the case, we have y plus 3 divided into y minus 2. Y goes into y one time. Y, 1 times y is y. 1 times 3 is plus 3. Draw a line and subtract. So that becomes negative. That becomes negative. So here we have remainder, negative 5. So this is 1 minus 5 all over y plus 3. Yes. So now when I integrate this 1 minus 5 over y plus 3, I can integrate the 1 that's with respect to dy, that this becomes y. I can integrate 5 over y plus 3, that becomes 5 times the natural log of y plus 3. See that? So then the same thing over here applies for the x plus 4 divided into x minus 1. So x goes into x 1 times. 1 times x is x. 1 times 4 is plus 4. We draw a line and subtract. So this becomes negative here. Becomes negative there. We have remainder 5. So this is 1 minus 5 over x plus 4. Don't need the answer sitting right there in front of us right now. Okay. So I have the left side is the integral of 1 minus 5 over y plus 3 dy. That's equal to the integral here of 1 minus 5 over x plus 4 dx. So the integral on this left side becomes y minus 5 times the natural log of y plus 3. That's equal to x minus 5 times the natural log of x plus 4, and then plus some constant there. Okay. So I'm going to get the x's and y's together. Since they're of the same form, I'm going to get the natural logs on their side together. So here what I have is y minus x. See, I'm going to write this as some plus that constant there is equal to the natural log of the absolute value of y plus 3 over x plus 4, and that's raised to the 5th power exponentiate both sides. So I get e to the y minus x plus some constant is equal to y plus 3 over x plus 4 raised to the 5th power. You can write this left side as e to the y times e to the negative x times e to the c sub 1. So let's say this implies this is e to the y, that's times e to the negative x, and that's times e to the c sub 1. You can write e to the c sub 1 as just a constant. This is equal to y plus 3 over x plus 4. That's raised to the 5th power. And so this becomes, do you see it? This is e to the y times x plus 4 to the 5th times some constant, say c, that's equal to e to the x times y plus 3 to the 5th. Here, that's where c is equal to e to the c sub 1. Yes.
And instead of like dividing, can you go up a little bit?
You say go up?
Yeah, please. Well, instead of like using the division and for improper fraction, can we say y minus 2 minus 3 plus 3 without changing the meaning? So it's still going to be y minus 2.
You can do that.
And if it's something, right?
I don't know. My go-to method is division. Yeah. That method there is to add a sophisticated 1, so it could be plus 3 minus 3, that kind of thing, over that denominator, y plus 3. That's fine. Yep, and that works too. But yes, let's see if I got time for one more. Let's see what this next problem looks like. Yes, I'm sorry. Well, I think that based on our time, that may be it. If anybody came in after I call the roll, make sure you stick around so I can get your name on the roll. Other than that, have a good one. There's a couple more problems that I'll finish up here, and then we'll get into 2.3 on Wednesday. Okay?